It's my pleasure and honor today to announce and give a brief introduction about today's presenter and speaker. It is Professor Voula Pantazopoulou. She is currently a professor and was recently a chair of civil engineering at York University, Toronto, Canada. And she has, as you must have read the announcement for this lecture, she has really a very rich and diverse background and experience, primarily academic, teaching at the University of Toronto, Canada, then at a couple of universities in Greece and Cyprus, and she's now again in Canada at York University. She is one of the most internationally renowned experts in reinforced concrete structures, and this topic that she's going to talk about today is just one of many areas that she is very, very proficient and competent in. So she did her PhD at the University of California, Berkeley, and during her career she has worked with many students and published more than 120 journal papers with a large number of citations. What is very important, she has been very active in professional communities in Europe as well as North America. She was active in participating and contributing to several technical committees in the American Concrete Institute, American Society of Civil Engineers, FIB in Europe, and Canadian Society of Civil Engineers. She is currently a member of the Bridge Committee, Technical Committee for Bridge Design in Canada, and is member of directors of the Board of Directors of Canadian Association of Earthquake Engineering, and International Director for International Association of Earthquake Engineering. So her field of work is concrete structures, but specialty is earthquake engineering. So she has many awards and accolades to her names. She has been she is a fellow of Engineering Institute of Canada, elected in 2019, fellow of American Concrete Institute, and received awards from ACI. So today she will be talking about novel materials and technologies and seismic retrofit of existing reinforced concrete structures. I would just like to mention that today, after Professor Pantazopoulou's lecture, there will be opportunity for you to ask questions. And after that, our sponsor for today's lecture, as you can see some displays, is SICA Serbia, and they are going to make a brief presentation about their products and also have some brochures to share. Your colleagues from SICA here. So thank you for attending, and let us welcome Professor Pantazopoulou.
Yeah, Svetlana overdid it a little bit, but I wanted to say that I am particularly honored to be here today. This place feels very much like home, and a home I mean Greece, despite the fact that I live and work in Canada. So next to Greece, this is the place which I feel closest to, and so I'm really honored and very happy to be here today. I have been working over the years on the emerging materials and technologies that have been developed in the last 30 years or so, and the opportunities that they have offered in earthquake engineering, and particularly in the retrofitting of existing structures, which is a passion of mine because a large part, about 65% of the built environment has been built, is categorized as older structures. We cannot replace them because they represent a huge investment on behalf of society, and therefore we have to do something about them. So nowadays, at this period, about 1.6 trillion euros is spent yearly in Europe alone, just for construction, and a large fraction of that is in infrastructure, non-building construction, and about a third of that amount is spent in rehabilitation and retrofit of existing structures. So it is really a very large market out there, and as such the material companies that produce innovative materials have a large share of business. However, the topic is a little bit on the graduate level for students, for civil engineers graduating from undergraduate programs, and there is a lot of jargon out there from the various codes and the various approaches and the various material industries, and therefore to avoid some of this confusion or to use a benchmark for the further discussion, I want to begin this presentation by a few key points of reference. So, because the presentation is related to seismic retrofit, to seismic engineering, I wanted to first begin with a simple reference point, which is what matters in structural seismic response. Let's figure out first what matters in structural seismic response so that we may be able to see how we can fix the existing structures with the opportunities provided with the novel materials. So for a given earthquake and soil condition at a given city or a given site, we have the demand, that is what the earthquake will require of the structure. And this demand is usually described in the codes in the form of an acceleration response spectrum. So in the horizontal axis, we enter the spectrum with the period of the structure, and on the vertical axis, we read off the acceleration that will happen about at the top of the structure. And of course, this multiplied by the effective weight of the structure tells us what is the force that the structure will attract during the earthquake. But the force is really not as significant as the amount of deformation that the structure will develop during the earthquake, because that deformation is telling us how much damage the structure will endure. And in order for us to determine this deformation, we really don't worry at all about the acceleration response spectrum. What we worry about is the displacement spectrum. This is the relative displacements that are happening at the top of the structure relative to the base, and they are very easy to calculate. How? We just take the corresponding acceleration that is to happen at the top of the building, we multiply it with the period of the building to the square, divide it with 4 pi squared, which is about 40. So it's the acceleration times the period squared divided by about 40, and we get the displacement. And that displacement is what we use as a criterion to determine or to anticipate the magnitude of damage that the structure will develop. So that is the first key point of reference. Given the earthquake and the soil conditions, we have the displacement demand, what the earthquake requires of the structure in terms of displacement. Another important attribute of the seismic response of the structure is how the structure takes that displacement. And this is represented by the shape of lateral vibration. That is usually well approximated by the fundamental mode. Although it is not actually the fundamental mode of response, it does, however, relate to the fundamental mode of response. So if you see large concentrations of displacement happening in a single floor, then you know that in that floor you are anticipating the damage. So the shape of lateral response is really telling us something about the distribution of demands throughout the structure, and therefore the tendency for localization of damage. Localization is a bad word in seismic engineering and earthquake engineering. Anything that localizes means that it is taken by one point in the structure altogether, and therefore that point will suffer while the rest of the structure will just be looking. So the morphology of the structural system determines both the fundamental period, which determines the displacement demand, and it also determines the shape of lateral response, which determines the tendency for localization of damage. And that was the demand side. In earthquake engineering, we are also interested in the capacity side, which is how much deformation capacity do the critical locations where we have large deformation demands, how can they how much can they take. And here is where the new materials can help us. How can the new materials help increase this deformation demand, the deformation capacity, sorry. So in order to understand the practical illustration of what I have been describing, consider these two houses. They were built in the same period in a part of Greece, which was damaged in 2008 by a local earthquake. The two houses were built with the same method, same technology, same period of construction. However, the bottom structure, which totally collapsed, what it had was the lower floor without infills, whereas the upper structure was infilled in the lower floor. So they both were subjected to the same earthquake, and it was determined that the top structure had a period of about 0.2 seconds. So when we enter the spectra, the top is the acceleration spectrum, the bottom is the displacement spectrum, we see that in terms of acceleration, this structure would demand about 40% of G, and therefore the base shear would be 40% of G times the weight of the building, the effective weight of the building. However, the displacement would be very, very small, less than 5 millimeters. So that's very small displacement, whereas in the lower building, the period would be estimated to be about 0.55 seconds. That's very large for a two-story building. And then if you see at the spectra, the red line that gives you that at the top spectrum, the acceleration spectrum, we would have about the same demand in terms of acceleration, therefore the same force. However, the displacement would be 30 millimeters. And the columns of that building in the critical floor were not able to take these 30 millimeters. That's why it collapsed. So what's the difference in terms of the shape of lateral vibration is shown over there. The green shows the shape of lateral vibration of the top building. The bottom shows the shape of lateral vibration of the lower building. And you see the concentration of the demand. This is the bad news. This is the tendency for localization, and this is what we want to get rid of. So in terms of retrofitting, when we start the process of retrofitting, the first job that we need to do is to determine, to assess the structure, to evaluate the structure, to anticipate what the structure will need to do, will be demanded to do during an earthquake. And so there are two ways to go. One is to develop global interventions where such are needed, only if they are needed, with the goal to reduce the seismic demands. How? By addition of stiffness. When we add stiffness, we always add strength. Stiffness and strength are the two sides of the same coin. You can't have one without the other. So by addition of stiffness and strength in critical location, you can then reduce the period and therefore the displacement demand. The other approach one would take, if such is needed, and usually that is always needed in older structures, is local interventions with the objective to improve the deformation capacity of the critical structural components. And I have to say that when you do global interventions, you usually improve also the deformation capacity, but that's not always the way to go, because global interventions are very expensive and they intervene throughout the building, so they disrupt the normal function of the building. So we need diagnostics to determine which way to go. Should we go for global? Are they needed? Or should we just stick to local interventions? What are the available diagnostic tools we have? Well, the first you have already learned in your undergraduate reinforced concrete design course. No mention to seismic design at all. It was called the sway index of a building. You all learned to calculate the sway index of a building. And that's the most reliable diagnostic tool for earthquake engineering, for the assessment of a building. If a building is a sway type building, then it needs stiffness, it needs global interventions. Another tool you have is to check the magnitude of the period. If if you have a very excessive period, a large period, then definitely you need to bring it down. You need to reduce the period. How do you measure the period? Well, there are instruments that you can take in the field, place them on the building, read the period under ambient vibrations, usually generated by a truck passing by. You need to increase these magnitudes if they have been generated by small ambient vibrations, because the actual structure during the earthquake, it will open all its cracks, whereas when the truck passes by, the existing cracks will not open. And we do that by taking the measurement and we multiply it with the square root of 2 to account for the fact that the stiffness of the structure is reduced by 50% when an earthquake occurs. So this is, for example, a building, a multi-story building, which was measured with the instrument, placed on site. It was found that the period is 0.56 seconds. That's very low, of course, and the owner was very happy, but we are not allowed to stay on that. We have to multiply with the square root of 2 to account for the fact that in an earthquake event, there will be much larger intensity vibrations. So we end up with a period of 0.8 seconds. That's less than 0.075 times the height of the building to the 3/4, which is the old calibrated expression that the Eurocode would give as anticipation for normal periods for such buildings, or the new Eurocode, which is cooking right now, it says we should go with 0.05 times h to the 0.9. In both cases, this building passes. So this building does not need global interventions. Another way is to look at irregularities in plan and in height. If we have irregularities, there is a good chance that we may need global interventions. And of course, we can always calculate or measure by placing the accelerometer at different heights of the building, that accelerometer that I showed earlier. You can measure the shape of the fundamental mode. And then if you see such things, then you know that something is bad, because this is the most critical damage index. It's telling you what's the potential for damage in the building. All right. A sudden change in the translational shape of vibration of the structure is the most significant effect in the generalized stiffness of the building, and therefore of the period, because the period of the building depends on the stiffness, on the generalized and the effective stiffness. For example, the typical lateral stiffness calculation is done as follows. You take the stiffness of every floor, which comprises contributions from columns, from walls, and from infills. You sum those up, and you multiply them with the change in the lateral shape that is happening in that particular floor, but that goes squared. And that creates a paradox in earthquake engineering. And that paradox is that the most weak, the softer part of the building controls the stiffness of the overall system. Okay, so if you have a floor that is weak, that is going to control. It's like Murphy's law. If anything can go wrong, it will. So if you have a soft story, a story where you have greater localization of deformation, then that really represents the stiffness of the entire building. All right. So that in this particular case, delta phi is the change in the shape, the lateral shape that is happening in the building, and it's happening in the lower floor. It controls the stiffness of the entire system. So in redesigning the building, we have as a goal in a global intervention to modify the translational shape of vibration to a targeted shape, a shape that we like, in order to eliminate the tendency for localization. The more uniform the distribution of seismic demands that we will get, the better will be the response. So what do? We have a good feeling of what should be the period. The Eurocode tells us what a period should be for a building of a certain height. So we can start with that. That's a good target value. If we are way above that limit, then we need to stiffen the building. So we can target the value of the period to be related or close to the value of the Eurocode. That will allow us to estimate the effective stiffness, and then if we remember that the effective stiffness is the sum of the floor stiffness is multiplied with the shape change to the square, we know then what to change. And actually, the best thing is to aim for a uniform shape. Of course, we will never get exactly to the uniform, the linear shape. But the closer we get to it, the more expensive the solution. So everything has to be done within reason. So as a general guideline, we aim for a uniform distribution of strength and stiffness among the members in any given story in order to minimize the tendency for localization. Here I show you the spectra that you saw earlier, but now I've plotted them differently. The vertical axis is the acceleration, the horizontal axis is the relative displacement, which you remember how we calculated it. And the green region is the acceptable region of design. The green line represents the building with a period as per the Eurocode. The yellow line represents a lower bound of acceptable design, which is the maximum value of period we are prepared to accept. The red line is the slope, that is, it's related to the period of a poorly designed building that we want to fix. So what we want to do is take this red line and bring it counterclockwise to fall inside the green region. The closer we go from the yellow to the green line, the better the retrofit. So, what should we target? We can target, for instance, a period for frame buildings of 0.1 times the number of stories, or we can target the period of the Eurocode. Okay? And for wall buildings, we have to go to smaller values. And if we target this, and we also decide what's the maximum allowable period that we are prepared to accept, that defines for us the design region. All right, having defined the design region, we are now about to design global interventions, and the question that we need to answer is how much stiffness to add? What should we aim for? And at what floor levels? These graphs show you what is the required effective stiffness of a multi-story building, and the dots correspond to the different numbers of stories, given the period which enters the horizontal axis. So, given the period that you want, you can determine what is the effective stiffness for this particular building. Of course, this corresponds to a unit mass, which you then need to multiply this quantity by the actual mass of the building in order to convert it to a stiffness value. And this here is a ready-made graph that you can use in order to determine what is the stiffness of the second floor compared to the first floor, the stiffness of the third floor compared to the first floor, the stiffness of the eighth floor compared to the first floor, that you need to improvise, you need to add in order for the structure to have no problem in terms of seismic response. Once you have determined that, once you know what's the stiffness of every floor that you need, then it's easy to do that. One familiar way of global interventions, which is very common throughout at least our region, is what we call jacketing, and jacketing with conventional concrete, where we add longitudinal reinforcement. The longitudinal reinforcement needs to be added in order to increase the stiffness and the strength. So global intervention means you need to add longitudinal reinforcement. Transverse reinforcement to provide ductility, and of course, because this is a global thing, it has to penetrate from one floor to the next. So it's very messy, as you see. But this is the prevalent method for global interventions. And then the question comes, what can new materials offer towards this retrofit objective? And the question is, what kinds of materials do we have in our disposal? Well, we have a number of new materials. First of all, we have FRP bars, which can be placed inside grooves. We call these near surface mounted bars. We have laminates, which can be introduced externally. They can be anchored on a structural member. That's longitudinal reinforcement, addition of longitudinal reinforcement. And any type of well-anchored longitudinal reinforcement will do for a global intervention. For local interventions, we have what I have written in red. So we have externally applied reinforcement in the form of FRP wraps, in the form of TRMs, Textile Reinforced Mortars, SRPs, Steel Reinforced Polymers, SRMs, Steel Reinforced Mortars. The steel now comes in the form of wires, pre-stressing tendons, straps, FRCs, Fiber Reinforced Concretes, Engineered Cementitious Composites, ECCs, and the most recent guy in the group is the ultra-high performance concrete. These are concretes of extremely high compressive and tensile strength. What are the available methods? We said we now have determined that in a global intervention we know exactly how much stiffness to add in every floor. What are the available methods we have? We said the jacketing, okay? But the jacketing means that we are changing the member dimensions. What else do we have? We have infills. These are traditional approaches. We have addition of walls. We have cross braces. This is a very nice solution, particularly for certain kinds of uses of buildings. Steel jacketing or external pre-stressing. All these methods written in black lettering do increase the stiffness and therefore the strength, and therefore they represent global interventions. In red, which are local interventions, we have confinement. Confinement is the essence of a local intervention. So what do we have? We have jacketing with externally applied FRPs, SRPs, TRMs, or UHPCs. If there is time in the end, I do want to talk to you a little bit about UHPCs because this is the future in retrofitting. And what do we use them for? Well, we use them to increase all the undesirable modes of failure in the building and also to increase the deformation capacity of components. We have a huge selection of materials right now in the category of FRPs, SRMs, SRPs, and TRMs. The P, the last letter, stands for polymer, so you can have fiber reinforced polymers, steel reinforced polymers, or fiber reinforced mortars, which are the TRMs, steel reinforced mortars. Again, these are the SRMs. And they come in a great range, okay? We have carbon, glass, basalt, aramid. We have even geonets, which are ideal for low-strength materials such as masonry. And they comprise polyethylene or polypropylene products. They come in the forms of, the FRPs can come in the forms of laminates, in the form of bars of pre-stressing tendons, and then in the form of the impregnated matrices, which are the matrices that you see with the voids. So we have a huge selection, and before we talk about how we use them, let's just review quickly some of the characteristics in terms of the durability of these materials. In the horizontal line at the top, what you see, the first 5 columns represent the various types of fibers. Basalts are missing, but they are very close to glass. So we have E-glass, S-glass, AR glass, alkali-resistant glass, aramid, C fibers, that is carbon fibers, and then the last 3 columns represent the various resins that can be used to impregnate these materials, and then the left column in the table gives you the various aggressive agents to which these materials need to resist. So, for instance, one is the water absorption. We don't want our material to be absorbing water. Their resistance in weak oxides, strong oxides, strong alkalis, weak alkalis, their response in temperature, UV radiation, to organic solvents, and then the resistance to ozone. All these are considerations. And of course, there is a line where I also give you the coefficient of thermal expansion, because that's important, particularly if you are embedding this material inside concrete, because all our life up to this point has been based on the ideal marriage between concrete and steel, because they happen to have the same coefficient of thermal expansion. But now, with these materials, we have to think, because they don't have the same coefficient of thermal expansion. Some may even have negative coefficient. So, there is a color code here. D, green letter D, means that the material is durable to that particular aggression. The P, red, is that it has poor performance to that particular aggression, and the M, the black, is indifferent, it's an average. And you see, by just perusal of the table, you see that the best materials are, of course, the C fibers, carbon fibers, embedded in the epoxy resin. So these are the best versions. Not that the others are not usable, but you have to worry about their resistance to various aggressive environmental agents. All right, so I said we have various materials. What they can be classified on is, of course, the matrix in which they are impregnated. For instance, we can have polymer matrices. These are very fast retrofits. The only problem they have is that sometimes they have a shorter service life. And then we have mortars for matrices, which are inorganic materials. They are cementitious. And in these, the various FRPs, TRMs, SRPs, etc., are impregnated. They have better durability and resistance to fire. These are typical fabrics that fall under this category. And you see also the metal strands, which correspond to the SRP. The SRP is also shown in the next second lower picture. And here is the SRP after removal of a few strands in order to make it perform like TRM, to be impregnated in cementitious materials. And then you can have them bonded or unbonded. These are different ways to classify them. I already talked about near surface mounted solutions. If you are adding a lot of reinforcement, better use this option. And externally applied reinforcement, which is particularly useful when you do either external adhesion of laminates or wrapping around columns. And then you can have other solutions where you use straps of tensile members around the member that you want to retrofit. And these are images from different solutions, different applications. I'm sure you have seen several of those in the literature, and these are again solutions on masonry structures. I want you to remember that masonry can also be retrofitted in the same way. And here are some various solutions on masonry walls, because masonry is particularly useful. The top picture corresponds to an unreinforced masonry wall. The second picture represents a wall that has been retrofitted in shear with horizontal straps, because you remember that we always put the shear reinforcement parallel to the shear force. That's the best way. So that's the case shown in the middle. Under lateral loading, this had the best performance. The bottom had X braces made of FRP, and of course here you have walls retrofitted with various layers of TRMs, and you can see that of course the response can be particularly improved. Then we also know that they perform very well as jacketing devices for retrofitting of reinforced concrete elements. Here is, for example, a very highly damaged column with, you see it at the top, it has been damaged under cyclic load and then retrofitted below with CFRPs. And here you see different types of response of such columns. The blue lines represent the initial response. The red lines represent the response after a retrofit. The first response and the last response are very good, because in this, the load history, in the first slide, the first graph, the load history was applied incrementally, gradually, representing a long distance, far-field earthquake. And after retrofitting, the response was recovered. The second slide represents the response of a column that has been subjected to a near-field earthquake, which has very huge pulses, an initial, that is, significant pulse, which caused yielding inside, spread of yielding inside the foundation, which, unless you fix, by just wrapping the column, you can't do much. You have to always go inside the foundation and try to recover the reinforcement, the anchorage. The last shows you again a case of a column which was reinforced with very sparse stirrups, so it failed in shear. This is the easiest thing to fix with FRP wrapping, because as long as we don't have strain penetration inside the footing to damage the anchorages, it's very easy to fix the part that is above the footing. The problems become when you have flexural yielding in the first phase of response with extensive yield penetration inside the footing, which you have to do something about before you retrofit. Here are methods to extend the service life of structures that had been corroded. Here is a program. There was several columns. We corroded artificially a large number of columns. Originally, they were designed as per the current standard for bridge engineering. You see the setup for the accelerated conditioning of corrosion in the left side. This figure here, shouldn't move. How do I show here? Maybe with this, right? Yeah. Okay. Sorry for this. This figure here shows the condition of the stirrups after the accelerated conditioning with corrosion. Here are three columns. The first is the pristine column, the column that had not experienced any artificial corrosion. This is a column after being corroded. You see the kind of damage. And here is the column which, after it was dried, very critical to be dried, it was wrapped with a few layers of glass FRP. And you see the response of that retrofitted column is the one shown in red. The blue is the pristine column, and the green is the column after corrosion. So you see that corrosion can be very devastating in the response of a structural component, and FRPs can help recover a large part of that. All right, and similar experiments conducted on larger scale columns. Again, you see the figure at the bottom shows you in very, very fine red line the behavior of a jacketed column, identical to the one that is shown in black, but the one shown in black was not corroded. The one shown in red was corroded significantly and then jacketed with CFRP layers, two CFRP layers, and of course the response under cyclic load was significantly improved. Now, all this experience, all this information has been going on for at least 20 years. There has been research going on intensively for at least 20 years, and it has been collected. In the most recent report of the FIB on FRPs, this is Bulletin 90. The previous bulletin was published in 2001. That was Bulletin 14. So there has been a lot of water under the bridge over these years, a lot of information collected. And this bulletin represents the benchmark, the reference document for the development of the provisions of Eurocode 8 Part 3 referring to the FRP. So it's useful, it's a useful document in order to see how the code, the new code, is going to approach this problem. The Bulletin 90 comprises a number of chapters, including information on the materials, on the basis of the design and structural analysis, on durability considerations, on bond, ultimate limit states for predominantly static loading and fatigue, serviceability limit states. Chapter 8 is what we wrote on ultimate limit states and seismic retrofitting, and then there is a chapter on detailing. So, I will just go very briefly over the chapters. How are we doing in terms of time, Svetlana? We are okay? Yes? Okay. So, in terms of chapters, so in chapter 2, there is a summary of the materials, and at the right-hand side, you can see the typical stress-strain response of the various types of materials. You see the CFRP is the best of them in terms of strength and stiffness. You see all the other materials that I have mentioned, and of course the lower horizontal line is the mild steel, the reinforcement. And there are various ways. There is lingo related to the way we apply the FRPs. So for instance, for the externally applied reinforcement, hand layup is what you see at the left where they wrap a column, prefabricated strips and shapes, near surface mounted reinforcement, pre-stressed FRPs. There are specific techniques by which this is applied. The basic requirements is, of course, that all the relevant codes are attended to. The basis of structural design, Eurocode 1990, design of concrete structures for 1992, EN 1992, then the general rules for seismic actions and rules for buildings in Part 3 assessment of Eurocode 8, and then the corresponding model code. What are the concerns? There are two concerns here. The first is to decide how to account for the effects of the additional reinforcement that we provide in the form of externally added reinforcement, and what is the development capacity of that reinforcement. Development capacity is this reinforcement. How much of its strength can it actually develop? Because we may be feeling good to be using a material that has a strength of 2,500 megapascals, but if the anchorage is not sufficient to support even 200 megapascals, that's all you're going to have, 200 megapascals. Okay, so development capacity, which depends on the anchorage, is the key. So I am going to focus a little bit on FRPs, because FRPs is one point of reference. UHPCs, these are the cementitious materials, the other point of reference in this whole range of materials, and everything else falls in between, combines properties from the two ends. So the FRPs, they can increase your axial capacity, the ductility, they can delay the bar buckling, they can improve the efficiency of lap splices, and of course increase the shear strength of a structural member, but also increase the diagonal tensile strength in beam column joints, and it does that primarily through jacketing, which provides confinement. So these solutions are all local interventions. FRPs can also increase the flexural capacity through the addition of externally bonded laminates or near surface mounted laminates or bars, and these are causing strength and stiffness increase, so these are global interventions. What is a local intervention? When is that thing needed? So look at this graph. This represents the typical response curve of an old member. The vertical axis is the strength, the horizontal axis is the deformation capacity of an old type member. Is this good? It is not good if the peak value is below the yielding of the main reinforcement. The main reinforcement has to be able to yield in all the structural components. So that is our benchmark, our point of reference. Can we yield our main reinforcement? If we cannot, we need to mitigate brittle modes of failure. We need to ensure that the existing main reinforcement will be able to develop its capacity. What is our basic method? Is jacketing through different materials. And how does jacketing work? It works by just confining. It doesn't do anything else, it just confines. Does not add reinforcement. That's a local intervention. So here is how the jacketing works, and this approach here is how the jacketing works when you use an FRP jacket. So if you cut through a circular cross-section, you reveal the forces in red that develop in the jacket, and the blue diagram represents the confining pressures that are developing inside the core of the column. The same exactly model works if instead of an FRP jacket you have a UHPC jacket, that is a jacket made of a cementitious material. It's very easy to calculate the lateral pressure in these cases. And the same, of course, holds if you have a rectangular cross-section, the only difference being that there is an effectiveness coefficient, because things are not as effective in rectangular cross-sections as they are in circular. And the expressions in the boxes show proposed, recommended values for the increased compressive strength of the encased material, the material that is inside, and for its strain capacity. So you have a direct relationship between how much strength you want and how much deformation capacity you want for your encased material with the FRP material that you're going to add externally. So that's your first design clue. You know what you want in terms of deformation capacity. You can figure out how much jacketing you need. So if we were to stop the lecture at this point, that's a significant takeaway. So how do we work for seismic? For seismic, we need to somehow relate to what a structural member does during an earthquake. So a structural member, let's say in a frame during an earthquake, does lateral sway. That means that it develops along its height a moment diagram that looks like the green diagram over there. So let's understand this diagram. So here is a column which begins from this position to this position, and this is the typical moment diagram that develops during an earthquake in a column. Then there is another column above. Here is a beam, and what happens is a reversal of the moments of the column inside the joint. So you can tell immediately by the slope of the moment diagram that you have a lot of shear in the columns, but you have significantly larger shear, maybe 10 times as large shear inside the joint. So, because of the symmetric conditions at the top and the bottom of the column, we work with half of the column because it's easy to solve. It has the same statics as a cantilever. So we can work with the half of a column pretending that it is a cantilever, although it is not. It's just half of a swaying column. And we can easily relate, or we can easily rather determine what is the ductility we want for the structure, because ductility means certain amount of damage for our structure. So for instance, a ductility of 3.5 means that we are going to have significant damage. Okay? Ductility of 1.5 means very little damage. So we can have a target for ductility in our retrofit. And once we have the target for ductility, we can figure out very easily the target for the ductility of curvatures. So the ductility of displacements for the building can be easily converted to a ductility of curvatures, and the ductility of curvatures can be easily converted to the strain capacity that we need for our material. And remember, I told you that there is an expression that relates the strain capacity to the confining pressure, and the confining pressure is directly obtained from the FRP, from the FRP amount. So you have a relationship to perform calculations. So our unknown is how many layers of FRP wraps we need. And our aim is always to ensure that whatever reinforcement we have in there will yield prior to the occurrence of a number of undesirable events. For example, delamination of the concrete cover, it's an undesirable event in the compression zone. Disintegration of our concrete confined core. So we need to increase the deformation capacity of that core to ensure that this disintegration will happen after yielding of the reinforcement. Failure of the lap splices and the anchorage, that's a bad thing. It gives a lot of flexibility to our building, therefore a large deformation demand. Diagonal tension failure, wherever that might occur, in the webs of beams, columns, in walls, in beam column joints. We also want to control the bar buckling. So these are our design criteria for determining how much FRP we want and where do we want to place it. So our starting point is, of course, the confinement. You remember that I told you there is a confinement effectiveness. I give you that expression for confinement effectiveness in the center bottom of the page. Remember that sometimes FRP, instead of being wrapped continuously around the member, you may want to put it in layers. That's also acceptable. And it's actually good in some situations where you worry about corrosion, because you want to ensure that the structure is breathing, that you're not trapping inside moisture that can keep the corrosion cell going without you knowing outside. And as I already mentioned, all the money is, if you go for the confinement, is in the anchorage of this thing. You don't want to have premature failures of your strengthening at the anchorages. You have two kinds of anchorages. Wrap on wrap, which is the situation at the left, that is an FRP wrap being anchored on a substrate, which is FRP, or FRP on a brittle material, on a cementitious substrate. So obviously this is much more critical, because you can think of what scenarios can happen. There, what you can lose is you can split the adhesive that connects one layer, anchors one layer on top of the other, but the adhesive is very strong, several times stronger in tension than concrete and in shear. So this is the most critical situation where the weakest link gives. The weakest link could be either the layer of adhesive or the cover of the concrete member. So you can have shear failure inside the cover. You can anchor it with these chemical anchors that you see at the top. So you drill a hole, you put this with epoxy, and then you spread the fibers of the FRP all around. That's a very good way of anchoring. Or you can even use towels. So the FIB Bulletin 90 gives you information about the bond strength of wraps and of near surface mounted reinforcement. The reason why you need this bond strength is because you need to be able, not just bond strength, you also get the slippage at zero residual bond. The reason you need this is because that quantifies the fracture energy of the substrate on which the FRPs is glued on, and that fracture energy enters the calculations for the development length. So, this is the typical situation where you have cracking inside the substrate. These are the typical conditions on site. The worst, the most vulnerable situations are situations, as I said, where you have a laminate glued on the cover of a structural component. You need to provide sufficient anchorage, if possible, with transverse wraps going over the end. The reason being that there you won't have zero moment, ever, because it stops closer than the end supports of a structural member, so you have a non-zero moment. And that non-zero moment means that you have curvature, and that curvature is causing the tendency for peeling of the laminate in the end. Okay, so these are typical expressions that you will find in Bulletin 1990, in the Bulletin 90 regarding the effective bond length and the FRP anchorage capacity at the end. You may also have the same phenomena happening near interior cracks. You may have the beginning of the delamination near an interior crack. So transverse wrapping over externally bonded laminates or chemical anchors are a must in order to enhance the development capacity and get rid of this design problem. Debonding mechanisms for FRP, near surface mounted FRP systems. What I showed you here in the previous slides was externally applied laminates. In near surface mounted systems, the resilience is greater. You can have a number of possible failure modes. For instance, you can have failure at the bar epoxy interface. You can have failure at the epoxy concrete interface. You can also have splitting failure that crosses the epoxy and splits the cover, the adjacent cover. So all sorts of such things may happen. The maximum tensile stress that your FRP reinforcement can take at failure is obtained from this expression, where here is the critical crack path that it can develop, and here is the fracture energy of the material in which it is encased. Now, going back to the seismic problem, having in mind that we have all these issues in terms of anchorage, that's the key issue for FRPs. What you need to determine is what is the usable strain capacity of the material. The manufacturer gives you strain capacities which are given at the last line of the table at the left, but you can't really use that in your design. You can use a smaller amount, which is determined as the lowest value that would lead to failure from among a number of possibilities. For instance, buckling of interior reinforcement. It can cause a rupture of your FRP. So you have a limiting strain capacity of the FRP, which is related to the setup that you're using, and that buckling strain capacity limits how much of your FRP you can use. Dilation of the encased concrete, it can rupture the FRP, particularly at the corners, which you saw we chamfer them, we rounded them up to minimize the stress concentrations, or we can have debonding of the FRP layers. All these values are strains that are limited by the mechanics of the failure mode, and they are generally less than what the FRP can offer. So Bulletin 90 recommend that we use a design value for the FRP strength, which is obtained from the characteristic value divided by a material safety factor, and at the same time multiplied by a factor that accounts for local effects. For example, the top table gives you the material safety factors for different load conditions, for persistent and transient loads and for accidental loads, both for the material itself but also for its bond strength, whereas the lower table gives you the corresponding thing, the material safety factor, but for seismic applications. And as I said, there is another factor, eta, which is reducing the availability of strain capacity of the material, which is accounting for local effects, for instance, local rupture. Okay, in terms of retrofitting for flexure, flexural retrofitting means that we are into a global intervention. We are strengthening the structural member. Not a very good idea, but sometimes we have to do it. Not a very good idea for seismic. For other situations, it is, of course, necessary. And of course, in order for this to work, it's got to be anchored from the point where you need the FRP, which is at the critical section at the base, further into the footing. Unless you do that, this is not flexural strengthening. So the locations that they show in red are the points where the FRP is expected to develop its peak strength. So more practical is, of course, to use near surface mounted FRPs. These require limited drilling, and of course always worry about the anchorage. In designing this, you need to worry about the hierarchy of the failure modes. You need to get rid of brittle modes of failure. Brittle mode of failure, for instance, is a shear failure. You need to increase the shear strength of your member to such a level that it will never be an issue before yielding or before reaching the flexural strength of its component. If the surface life serviceability limit state is governing your design, you'll end up putting a lot of amount of FRP, more than if an ultimate limit state was controlling your design state, and therefore you need to take additional measures to strengthen against brittle mechanisms of behavior. And you remember your bond at the interface is always limited by what the concrete can do. In terms of flexure, you always want the reinforcement to yield first. You can accept to have concrete crashing before FRP failure, or you can accept to have FRP failure before concrete crashing. These are the two situations shown here, but the steel must have yielded in order for this to work. And you should never go to a normalized compressive section depth. A depth of the compression zone should never be greater than 0.45 in order to have some ductility in your failure at the ultimate limit states for concretes with strength of 50 megapascals in cylinder strength, or less than 0.35 if you have higher strengths of concretes. For seismic application of global interventions, of course, either near surface mounted, which are shown on the very left, or attachment of laminates at the extreme faces of the structural member, you have to ensure the redundancy of the retrofit, and you ensure that redundancy by transverse wrapping. You have to ensure that this is not going to fail under the repeated cyclic loading. In terms of the ultimate limit states for seismic, you also need to be able to ensure that your member will develop its rotational capacity. The rotational capacity can be checked by considering the concrete, the wrapped concrete, the encased concrete in its enhanced state. That is, we said that wrapping increases the compressive strength and the strain capacity of the material. If you account for this, you will increase your rotation capacity, and that will also enable you to satisfy the requirements for the ductility that we mentioned earlier. There are two ways to go for this. Remember, always the objective is to determine how much FRP material you need. You can use this empirical expression that shows you, gives you what is the displacement ductility as a function of the FRP material that you're using. This is the FRP contribution. So if you have a target displacement ductility that you want to develop, you can figure out how much is rho FV, the volumetric ratio of your FRP material in order to achieve it. Or you can also go with the Eurocode 1998 Part 3, that's Eurocode 8 Part 3, which includes the expressions for rotation capacity of Professor Fardis, in which case the contribution of the FRP is this last term, and that then has to be done iteratively. Another thing that we said is you need to mitigate all brittle modes of failure. Brittle modes are, as I said, shear strength, shear failures. To enhance the shear strength, you can wrap the material, you can wrap the structural member, either continuous wrapping or in layers. If you cannot do a closed jacket, as is shown at the top, but you have to stop, let's say, at a certain depth into the compression zone, then you do chemical anchors or other forms of anchors to ensure that this FRP transverse reinforcement will be able to develop its strength. To determine how much you need, well, to determine how much you need, you go with the classical approach for shear design. You have an initial shear resistance, that's a VRD node term, that's what you have. And VRD is what you want, how much you need. The difference between the two is what the FRP would need to take. And in order for you to determine how much the FRP would need to take, this is the expression for the FRP contribution. And in that expression, the unknown is the rho, the amount of FRP that you need to add. Whether you go with a full fabric or whether you go with strips. And of course, you need to account the anchorage conditions of your FRP jackets in order to see how much force you are going to put in them. Another thing that works with FRP is clamping of lap splices. So you have two bars lapped, usually at the base of a structural member in old construction. If this is not clamped by transverse reinforcement, it's going to slip and you're not going to ever be able to develop the strength of your reinforcement. FRP jackets help that, because as the bars slip against each other, they dilate, they try to increase, to create space in order to slip because they are ribbed. And that space engages, that slippage engages the transverse jacket. And by engaging the transverse jacket, this returns back to the bar through a confining pressure. And so there is a very simple frictional mechanism that enables the clamping action. And so you can actually determine how much bond strength you need in order to develop your reinforcement. And as you will see, there is a term, the last term in this expression, which tells you what is the jacket component. And therefore, if you know what's the strength that you need, you can figure out how much jacketing you need to add. And then you also need to preclude buckling of the encased reinforcement. That's the most difficult thing to do, because reinforcement in compression tends to buckle if you don't have frequent TRMs. So you can do two things. Either eliminate the cause of buckling. What's the cause of buckling? A lot of lateral sway in the building. You reduce the displacements of the building. That's a global intervention. Or increase the deformation capacity of the reinforcement. How? By confining the concrete, which is next to it, so that the concrete can take a greater share of the force and a lesser share will go to the compression reinforcement, and therefore the buckling onset will be delayed. It will never be precluded. It will be delayed though. And remember, of course, that as the reinforcement buckles, it tends to create stress concentrations on the jacket and therefore tends to cause rupture. There is, of course, the strengthening of joints, but I don't want to stay too much on the joints because that's a very esoteric kind of subject. But again, there are ways that are given in Bulletin 90, which gives you how to detail this thing. And so this is the FIB Bulletin 90. A new bulletin is being under preparation with examples on these applications, on this guideline framework. So very soon you'll have a book of examples that will tell you how to use all these guidelines. The guidelines are in line with the Eurocodes and with Model Code 2010. At this point, I think that I should stop, although I had a few slides on UHPC materials. Svetlana, should I stop?
Just if you have interest of time, maybe just a few minutes, a little bit of explanation, but just a few.
Okay, so a few years ago, the engineered cementitious composites came about. What is interesting about these engineered cementitious composites? That they are strain hardening in tension. That's unheard of for concrete. So in this figure that you see in the left, if my mouse works, so in this figure you see the tensile stress versus tensile deformation of this class of materials, this new class of materials. The red line gives you the response of common concrete. The blue line gives you the response of FRC, fiber reinforced concrete. The green line gives you the response of this new class of materials. So you have suddenly a new store of capability in tension, and considering that all the wraps or the jacketing is working in tension in order to confine the encased material, obviously these products are a great opportunity. They have very large deformation capacity. You have all seen this picture at the lower left, I am sure. These are the new materials that have come about. And this is a comparison between two columns containing the same amount of longitudinal reinforcement. One is reinforced for ductile seismic response. The other has no transverse reinforcement. And you see their response at 10% drift ratio. So there are several such materials, but I don't want to stay too much on these materials other than just to show you a picture of retrofitting with this class of materials by just replacing the cover of the structural component, and you can enhance significantly the strength. However, recently, a totally new version of engineered cementitious composites has come about, which is called ultra-high performance concrete, which combine the characteristics of self-consolidating concrete, fiber-reinforced concrete, and high-performance concrete. They contain fibers. For instance, this cylinder gives you the volume that is taken by half a liter of water. The lower line, the black line where it says 500 ml, gives you half a liter of water. And the red line, which is just a fine portion higher, is what happens when you add 2% of the volume of the fiber. So you see lots of fibers, but they are only 2% of the volume of the material. What kinds of fibers are these? They are very fine fibers. Their typical length is about 13 to 20 millimeters. Their diameter is a fifth of a millimeter, very fine. And here is a concrete that has been reinforced with these fibers. How does it perform? Well, the top graph shows you the evolution of the compressive strength of this material. And if you look closely, the blue line is the laboratory value, the red line, the orange column represents the field value. If you look closely, we are talking about strengths in the range of 180 megapascals in compression. These are huge strengths. The most interesting aspect, though, is the tensile strength. So you see the evolution in time with curing of these materials in tension. So you see that we have strengths in tension of the order of 11 megapascals or more. So suddenly, this has opened up huge opportunities, particularly in bridge engineering. The number of bridges that are constructed or retrofitted by UHPC is continuously increasing. But also it has given huge opportunities in architecture. So many interesting monuments, architectural signature structures have already been constructed. And this is considered to be a truly new building material that architects and engineers are using to push the limits of their design. So here are different cases of monumental structures throughout Europe and North America. This is a typical stress-strain response of these materials in tension. Tension. The horizontal axis is a tensile strain, the vertical axis is the compressive strain, and this poor dotted line down here represents the conventional concrete. So we are talking about significant changes. So these materials are extremely durable to aggressive agents. They are capable of supporting service lives in the order of 150 years without maintenance. So this plot here up there represents the response of conventional concrete in the red bar, high performance concrete in the blue bar, and UHPC in the black bar to various events like salt scaling, chloride ion diffusion, chloride ion penetration, etc. They have very little permeability. And of course, their response, just one moment, Svetlana, their response to corrosion is very low. Under accelerated corrosion, they do not allow anything to pass through. What I wanted to show is jacketing with these materials. And I am only going to show a picture of damaged columns after being subjected to accelerated conditioning, corrosion condition. And here is their typical response. The interior cycles represent the original columns, and the exterior cycles represent the seismic response of these columns, either after being retrofitted, that is, after removal and replacement of the cover, or doing that after they have already also been damaged to seismic load. There is practically no difference. So I want to stop at this point, and I want to thank you very much for your attention. Sorry for taking all this time, and I hope that you found some interest in all this.
Thank you very much. I think I have to join you on the podium because of microphone. We don't have extra microphones so that we could report. Thank you very much for a very interesting and presentation with lots of information. I hope that it will be okay. As usual, we do post along with the video recording. We post the slides, so the colleagues who are here and also those who are not unfortunately present will have opportunity to see. But at this moment, we have time for a few questions since we have a short presentation and by the colleagues from SICA. So, any questions from for Professor Pantazopoulou? Please feel free to ask any questions that you might have. Okay.
I really want to thank for this excellent presentation, and I'm happy that we had this extra time because at the end we heard something that is really impressive about these new materials. And the first thing is, the first question that I want to ask you is, what is the current availability of these new materials, ECC?
There are lots of materials out there. They come pre-packaged. SICA has one of these materials, but there are several other products. And they are widely available for bridge engineering in particular. What we are doing is using them as a retrofit opportunity for cover replacement. We just remove the cover and we replace it with this. It's highly flowable, contains 2% steel fiber, but it is extremely flowable. If you look at the picture here, this is the two-minute flow rate of these materials. And as such, they are very, very useful for casting, let's say, jackets. They are very available. Actually, first of all, the French had been the pioneers in this. While the rest of the world was sleeping, the French had already issued a Eurocode for these materials, Eurocode 2. So they are out there.
Yes, and about the price?
The price is expensive, but of course it's coming down. It's the same thing as with the FRPs. When we started with the FRPs in 1995, they were expensive. As more and more non-proprietary materials are entering the market, the prices go down. I have included in the slides one mix design, for instance, for this. You can make it.
Yes, another thing that I want to ask you to go back to the beginning of the lecture is about the strategy we are approaching the existing buildings in order of making the criteria what is to be retrofitted, what is to be strengthened. For example, in our current regulations, we have this criteria that if we are constructing the building and if this building is for public use, it should be brought to the current demands of the Eurocode, which is very difficult in some cases. And the other buildings, which are not public attendance, public use, should be kept in this shape that they were designed at the moment that they were designed. And what are experiences, you recommend this, experiences, for example, in Canada or other countries, I know that's connected with money and economical strength, but...
What is the experience in this? Well, that's a general framework that you want to bring them to the current standards. That's meaning that you want the building to be able to withstand, let's say, the current seismic demands. Okay? So suppose you want them to have a ductility of 3.5. Okay, so there are ways to increase the ductility without changing the building overall if you don't need to. You need to determine whether the building needs global strengthening. or whether the local interventions will do.
Yes, well, this public buildings, practically you're obligated to do this kind of sectioning of the building, but it's not the case in some other private buildings.
Yes.
And that's very, very different, because there are a lot of answers, a lot of questions after the Turkey earthquake here in Belgrade. All the press was talking about it, is Belgrade safe, all the Belgrade buildings safe. Of course, completely different situation and everything. But I understand that there is a very big question: should this matter be left only in the hands of local investors and their private money, or should it be some kind
Definitely
of
there should be a guideline by the state how to do that. But from an engineering perspective, the reason why buildings fall is because of the tendency for localization of the demand in a few places. If you manage to distribute the demand so that everybody takes part in the party, then buildings is unlikely to fall. So this is an engineering decision. It cannot be prescribed. So what we are discussing here are ideas from an engineering perspective. So the code may tell you, yes, you need to reach current standards, but as you saw in Turkey, even modern buildings collapsed. The reason was that there was a tendency for localization, and then the members where the deformation localized were not detailed for that thing, or the quality of the materials was very poor.
Okay, thank you very much.
Thank you.
Yeah.
Maybe you can approach also the interior.
Okay. Thank you. First of all, thank you very much for this extremely interesting presentation. For me especially, but I'm sure that the other people share this feeling. This combination of seismic analysis with strengthening methods and retrofitting with additional spice of new materials makes this presentation unique, I would say, in the whole series of SUZI lectures. Yeah. So my short question is, how do you deal with fire protection in case of externally FRP laminates use? Because we have very strong fire regulations here in the country, so it's an interesting question for me.
So your design, when you have to consider fire, is to ensure that the building will be able to carry its own weight without the help of the FRPs, right? So that is a guide, a general guide. These materials are not very good in fire if you use polymer impregnation. But if you use TRM in the TRM version, that is mortar impregnation, mortar matrix, their life under fire is significantly increased. Okay, so we are talking hours, of course. Of course, here we are not talking about days or whatever. You just need enough time to evacuate the building. Yeah. But this is one of the limitations of the plastic, of the epoxy, if you use epoxies.
Okay, thank you.
But the epoxy resins are better in heating than the vinyl ester or the other resins. So if you go with the best epoxy, your life will be long enough for the structure to be evacuated, and the objective should be explicitly in your design that the structure should be able to take its own weight and all its permanent loads without the FRPs. So that if the FRP is not working, the structure still will be able to carry its self-weight.
Okay, thank you.
Thank you very much.
Thank you.
I think in the interest of time, we still have a presentation by Sika, so we come here. We have a small gift for you from SUZI. So it's SUZI gift, and hopefully you like it. You open it later, but I hope we managed to satisfy your taste.
Thank you very much. Thank you.